Hello friends, in continuation with the last lecture that we have talked about the width of the depletion layer. Now in today's lecture we are going to talk about the depletion layer capacitance. Okay, depletion layer capacitance. Capacitance, we know that capacitance is a charge storage device, right? So but now within the depletion layer we are going to talk about the how much is the capacitance. So the depletion layer capacitance is defined to be as a dq by dv and is represented with the cd. So the depletion layer capacitance, d stands for the depletion layer, okay, is equal to the dqd by dv. Now, when we are trying to bias that depletion layer or the p-n junction, at that time, how much amount of the charge is induced it, and when the charge, when there is a small change in the applied voltage or biasing voltage, then how much amount of the charge is getting induced inside it is given, or change is given to be the depletion layer capacitance. It is also equal to the epsilon s upon wd. Okay. Now here this dqd is nothing but the incremental depletion charge on each side of the junction. Okay, each side means that this is the p-n junction. If it is, then if it is p and n, so on the both the sides it is getting changed, because either side there are that majority charges are different ones. So that charge gets increased by the dqd, okay, on the each side of the junction, so that the total charge has to be conserved to be the 0. So upon incremental change in the some applied voltage or the biasing voltage dv. So for the one sided abrupt junction, okay, for the one sided abrupt junction, the capacitance per unit area, okay, capacitance per unit area, capacitance per unit area is actually given by the cd per unit area actually is equal to epsilon s upon wd. Okay, so we can substitute the value of the wd into it, okay, and that will give us the value is equal to q epsilon s n upon 2 into bracket psi bi minus v minus 2 kt upon q raised to half. Okay, this is what we have seen in the last lecture as well, where wd is equal to 2 epsilon s upon qn into psi bi minus phi minus 2 kt by q. So whatever we have seen here, there was no application of the voltage, so this phi was 0 in the earlier case. So do remember it. Okay. So I can give the question name cd as this as a 1. Okay. So here this phi can be positive or the negative depending upon the whether it is a forward bias or reverse bias. Okay, positive, this is for the forward bias and this is for the reverse bias of that p-n junction. Okay. So the result of this depletion layer capacitance can be seen in the your our diagrams are there, but that graph is complicated. So if you just try to rearrange the terms inside it, I just try to rearrange the term that 1 by cd square is equal, I just try to remove the square root on the uh, right hand side. So that will give us 1 by q epsilon s n into psi bi minus phi minus 2 kt by q. Okay, just squaring it. this, so I write down this equation number 2. So try to divide this equation with this, so we will try to understand that the if there is a small change in the potential applied, then how it affects on the its behavior. So just try to differentiate with respect to phi. So how much we get it? D by dv of 1 by cd square is equal to minus of 2 upon, because this will give 0, this gives us 0 independent of the phi. So because we are most interested in the smallest change in the biased voltage, so q epsilon s into n. So this is equation number 3. So it is clear from this above two equation that the if we try to plot 1 by q, okay, 1 by q, plot 1 by q versus phi, then the results into the straight line, okay, results into a straight line, okay. And how it is, okay, if I just try to plot the 1 by q versus, or 1 by c square, sorry, 1 by cd square, okay, 1 by cd square. So I just try to plot the graph of 1 by c square versus phi from this diagram, okay. Here 1 by c square or cd square versus phi. So how much is the this is a negative plot, right? So that I am just trying to plot it, because this derivative gives us the slope, okay. This is the slope of this graph, okay. So do remember this is so slope. So what it can give us, okay, it is just trying to get like this behavior, and if you just try to extrapolate it to, then this is psi bi minus 2 kt by q, okay, at this point, okay, at the point of the intersection, okay. Or else the slope what we can expect to have like this behavior, okay. So 1 by c square versus p, this will yield us in the built-in potential and the doping density n, can give us the information. Okay, so the slope gives us the impurity concentration. So the slope, what is it? Slope is equal to minus 2 by q epsilon s into n. N is nothing but the impurity concentration, okay, impurity concentration of that particular substrate. And if you just try to extrapolate, okay, extrapolate to the 1 by c square, extrapolate to 1 by c square is equal to 0, gives us the psi bi minus 2 kt upon q, okay. So this is the value we will get it from the extrapolation. And how much is the slope? We can get it, okay. This slope is see, slope is minus 2 upon q epsilon. So q and epsilon is a constant one, so obviously and minus sign is also there, so it is proportional to the 1 by n. So slope is proportional to the impurity concentration, inversely proportional to the impurity concentration. So for the forward bias, the diffusion capacitance, so in case of the forward bias, what happens that, okay, here we can have the positive potential on this side and negative potential on this side. So what will happen, the more number of charges, so the depletion layer will go on increasing in the forward bias. And so what will happen, in addition to the its depletion layer capacitance, there exists diffusion capacitance as well, okay, in case of the forward bias, okay. Now note that here the semiconductor potential and the capacitance voltage that are insensitive to the changes in the doping profiles that occur in the distance that less than the d by length, okay. D by length is the one of the new concept which is coming, that is d by length, okay. Do remember it, okay. We will talk little more about it in details, in depth, about the debye length. This is something like is related to the when we are having the some material having some one of the majority carriers, and if you try to uh, place the oppositely charged uh, plate nearby it or oppositely charged nearby that material, then how the electric field lines are developed within it and how they are just trying to change abruptly within that material gives us the debye length, and how long it extends within that material gives us the depletion debye length. So that's this is actually the characteristics. Debye length is the characteristics length of the semiconductors. Okay, this is a characteristics length of uh, characteristics length for the semiconductor, and is defined. I am just actually defining the things, that is LD is defined, okay, defined is equal to epsilon s kt upon q square n, is also can be equal to the epsilon s kt upon q n beta th. This is equation number 4. So, this is the debye length gives the idea of the limit of the potential change in response to an abrupt change in the doping profile. So, what it gives us? Okay, it gives us uh, an idea of the limit over what? Of the potential change in response, potential change in response to an abrupt change in the doping profile, change in the doping profile. This is what we call it as the details of the debye length, okay, what it gives us. So, consider the case where the doping profile has a small increase in delta n. Okay, just try to understand that the how this doping profile gets changed with some uh, change in its delta n, or the impurity just getting changed. Okay, so the small increase, that is delta n, is the small increase in impurity concentration in the background of in the background of ND, donor impurities, and corresponding change in potential. Okay, corresponding change in potential, that is built in potential delta psi bi, or sorry, change in its potential, that is psi I, and it is represented with psi as function of x near the step is given by, okay, is given, that is nothing but the small n is equal to capital N d exponential of delta psi I q upon kt. Okay, so yeah, so try to differentiate this change in potential twice, so that we'll get the will reach towards the its electric field. Okay, so the d2 delta psi I of x by dx square is equal to minus q upon epsilon s, and just try to rearrange the terms in this case, and substitute the value of the its density, it is nd plus this small change in the nd minus n. Okay, so this will result us into the q n d upon epsilon s, and then I'll just take out the n d common, 1 plus delta n d upon n d minus n upon n d. N upon n d will give us the exponential of delta psi I q upon k t, okay, that's q upon k t. Now, if suppose this is very small, then we can express it if this delta psi I q by k t is very less than 1, then e raised to x is equal to 1 plus x if x is very less than 1. Okay, this is the expansion can have for this series. So, substitute these values over here and try to rearrange the term, that is minus q, minus n is missing, q n d upon epsilon s to 1 plus delta n d upon n d minus of 1 plus delta psi I q by k t. Okay. So, this is what we can get it from the equation. So, this minus 1 get cancelled with this plus sign, and what is remain, if this delta n is very small, okay, delta n is very small, and what we will get it, that is by n d will be very small. So, what we will get it is approximately equal to the d2 psi of delta psi I by dx square is approximately equal to the q square. This negative sign will get positive sign on this side. So, q square n d upon epsilon s into k t, okay, into delta psi I. So, this is equation number. So, its solution has a decay length which is given by the above equation in equation number 4, that is somewhere here. So, decay length is given by this way, this equation. So, this implies that the doping profile changes abruptly, okay, doping profile changes abruptly in a scale less than the d by length, in the less than the d by length, and this variation has a no effect and cannot be resolved. So, and also if the deflection width is smaller than the d by length, deflection width is smaller than the d by length, the analysis using the Poisson's equation is no longer valid in that case. So, if you just try to look at the thermal equilibrium, the defletion widths, depletion layer widths of the abrupt junctions are about 8 times the d by length in case of the silicon, and 10 times in case of the gallium arsenide. So, the d by length as a function of the doping density for the silicon at the different temperature can be seen on the your what we call it as reference books. So, even if we have the doping density of the 10 raised to 16 per centimeter cube, the d by length almost goes up to the 40 nanometer. And for the other dopings, what we can say, LD can be varied with the 1 over square root of n, 1 over square root of n, and that is the reduction by the factor of 3.16% per decade, but that is some kind of the numerical part of it. So, do remember for this.